And I think that, no, I can do this. There we go. Now let me share my window. There we are. Okay, wonderful. Now let me find all my other windows now that they all moved around. Okay, great. So again, welcome. Hopefully everybody had a chance to sign in and answer the few questions that we have on there. We don't have an inclusion question today. We often have little inclusion questions at the beginning, but today we're going to jump right into it. We have actually quite a lot to cover. So it looks like we also do not have any special announcements today. We did get evaluations from our last session. And so we review those evaluations and we appreciate any feedback that we get. We're going to have another one today. And you know, please don't be afraid to be critical, because we really do want to know what we can do better. We see that these are the statements that we asked everybody on a scale. So what we see is a lot of people feel confident on how to teach scientific explanations. A lot of people feel confident on how to, or felt confident on how to try out the phenomenon in their classroom. And if there's one thing that, I'm sorry, I had that backwards. A lot of people understood the big science ideas. If there's one thing that we maybe want to work on a little bit more, maybe work on the actual teaching of interactions, how to apply what I learned today in the classroom. But we see a lot of positive responses here. Using models, we see a lot of agrees, but a smaller number of strongly agrees. So we'll continue to collect feedback, but the narrative questions are probably the most informative. So what we found that people found most valuable was using the lessons in Schoology, the resources that were shared, showing how the resources are laid out, the websites, the materials, and the group resources, and the digital resources like the stamp gallery. Some things that people asked us to improve upon. We're adding a recording. We did that. So we will do that after every meeting. We will post the recording. We posted it on Schoology, and we also will make sure that we index those and post them on our website. Some people really valued the times working as a student going through Nearpod. Wanted to see more examples. And generally, most of the comments that asked us to improve upon things was basically it's a lot of stuff to take in 2 hours. And you're right, it's a lot of stuff to take in 2 hours. And we're trying to cover the curriculum and get you prepared to teach it. So, and another thing that was mentioned was that I did refer to some of the tutorials that were posted last time. And somebody said they would prefer to just cover it during the PD rather than referring to a separate tutorial. And that makes sense. You're getting paid for the PD time. Let's give you what you need during the PD time. Some things that people ask for in the future are more Nearpod, EGI, and these are things that we may look to in the future for the next few weeks or for the next few sessions. We'll be going over the investigations in order, and then we do have some time to cover some more of these things like EGI, student engagement techniques, especially for SDC classes, more EGI. A few people asked for that. Media supports, pedagogy, time management, and how to integrate the interactions website with Schoology. And that's something we're really working on is getting the two resources or the two platforms to work together really well. So that said, let's look at our website. Oops. Actually, let's continue through that. So our objectives today are to continue to this transition from distance learning to in-person learning, because a lot of the stuff that we did a lot of stuff to support distance learning, and now we have to come back to just using Schoology with students, doing a blended classroom model. We're going to do an overview of investigation 3 in the first half of today, and then investigation 4 in the second half. And we are going to look at how to administer and grade CER responses through Schoology. We actually get to the point in investigation 3 where students are required to provide a CER response, and they actually do a reading on CER, and they are going to be expected to do more of these in the future. I think a lot of people are probably familiar with the term, but just in case, CER stands for claim, evidence, reasoning, and it applies to a couple of different science and engineering practices. It's like explain phenomena from evidence, and it can also apply to the argumentation practice as well. But so it's a good technique to use in science, and it's used in a lot of other subjects. Those who have not heard this from other teachers or from their students, CER is taught in social studies, English, but we use it a little bit differently in science. Our evidence is a little bit different. We're not just taking textual evidence from the reading. We're using experimental evidence. Our reasoning then is also different. So CERs, so students may think they know CERs, but it is important for them to learn that science is not necessarily the same as every other subject. So here's our agenda for the first half, and then we will have a separate agenda for the second half. We'll take a little break at 4:55. Here's the agenda for part 2. As I said, in part 2, we'll go over investigation 4, and Mike will go over how to analyze student work. If you're not already a member of the Interactions Teachers Group, please make sure you join it. If you're not a member, maybe you can post in chat. Maybe we can post the access code, because I'm gonna so you don't have to type super fast to try to get it in. Now, Unit 1, well, here's Unit 1. So we are in investigation 3 right now. We started out learning about interactions between positively and negatively charged objects and between similarly charged objects. And then we looked at how these objects have fields around them and how the fields are more powerful the closer you are to the object. Then in investigation 3 is really about looking at the nature of matter. So we look at the ancient Greek version of matter, is that it was this continuous model. And that evolved into a particle model. So most students have heard of atoms, have heard of molecules, even protons, electrons, and neutrons, but their concept often, they don't really get how things go together and what these particles are. And if you start using the word particle, they might not get it. So we really dig into that and spend a whole investigation establishing the particle model as valid way, the correct way to look at matter. And then in investigation 4, again, we'll talk about that in the second half. We see some stuff about indirect observation. Well, we'll talk about that in the second half. And then investigation 5, we put everything together. So investigation 3 is, what are all materials made of? That's the driving question. What are all materials made of? So let me switch this to well, actually, let's go to the website. I'll paste the link in. Oops. So this will be, we'll do a little overview of the interactions website. Let me go to the home page here, and I'll paste that link into chat. There it is. Okay, so this is our interactions website that we continue to work on. And so you may see that there are some clear visual changes, but there's also some content. There are some content updates as well, and we'll continue to make updates throughout this year. I want to focus today on the curriculum section. If you look at the left side of the website, you see that there's a menu there. And if you click by curriculum, you see that the curriculum section is actually divided into several different sections. Now, within the main page of the curriculum section, we do have that tutorial on how to add assignments to Schoology. If you haven't done that, like if you only do that once a year and you need to go back and review it, there's a little tutorial here to help you out. And we also talk about the overall structure of interactions. There is a pretty detailed unit by unit summary here. Sorry, my computer is rather slow to load. So we have this it's called a cheat sheet, but it's really a pretty good, well, not pretty good, it's really a good detailed breakdown of the entire year. And then we have just a list of how long you might expect to spend on each activity if you do them all in sequence. These numbers are not super accurate. I would guess that you will probably take more time for most of these than is listed here. But these are the times that were suggested by the curriculum writers. And I think most of us in LAUSD, if you're really making sure that students are understanding it, especially since we have a lot of English learners, we have a lot of special ed teachers teaching interactions, we have a lot of option schools using interaction. So we tend to go a good bit slower than this, but it gives you a good overview of how all the activities lay out, and you could plan it out yourself based on that. There is also a suggested pacing plan on another link. Okay, having some computer problems. So I'm not going to go through each of these. Maybe I'll go through them again in the second half. Maybe I'll restart my computer, or I can't restart it, but maybe I'll close some things out during the break. But but go ahead and click on the planning resources and guides link under curriculum, and that will show you a page with all of the investigations laid out. And I'm sorry, like I said, my browser is freezing out. There we go. So from the, let's see if I can get it to reload. Okay, so from the planning resources and guides page, this is a good overview of all the resources for all the different investigations. There's a key up here on how to use this guide. And then each unit is laid out here with these images. We see each investigation laid out. And the thing that I show during these PDs is the planning guide. But we also have Schoology lessons for everything in interactions. And we have Nearpods for everything in interactions. So we have multiple ways multiple methods you can use to deliver the content. You can add the Schoology lesson straight to your course. You can even open the student workbook as Google Slides if you want, and share that with students. You can use the Nearpods. Most of these are duplicates of each other. It's just a matter of what you prefer. So please click on the unit 1.3, the title there, actually not the title, but the planning guide. Underneath the title, underneath the image, click on the investigation 1.3 planning guide. So the overview of 1.3 is going to be pretty quickly. It's going to go pretty quickly because we don't have a lot of simulations in this. It's a lot of, you're going to have a lot of discussions with students. They're going to do some readings, and again, the idea, the driving question is, what are all materials made of? And the big idea is to understand, it's right here at the beginning, particle versus continuous model of matter, to get students to understand what the particle model of matter is and why it is the accepted model of matter. We start out in activity 1. We start out with what they call a thought experiment, but then there's also a demo. So the thought experiment is, well, what if I cut a piece of paper in half? Then I would have 2 pieces of paper. Then if I cut those in half, then I'd have 4 pieces of paper. And then if I keep cutting it smaller and smaller and smaller and smaller, I get smaller and smaller pieces of paper. And then we ask the students, well, is there some point at which I could cut it and it would no longer be paper? Or do I just get smaller and smaller pieces of paper forever and ever and ever? And then we have a nice, rich discussion on that. I don't see a lot of people on the planning guide, so I'm just going to post a link here in case anybody had trouble finding it. So I posted the link in chat. There we go. I see people opening it up now. Good. So we have this big discussion about, the continuous model, the particle model. We talk about the history of it, that, Aristotle really believed in this continuous model of matter. And Democritus introduced the idea of the atom. And then we talk about which one is correct. And we look at a lot of images, there's a lot of models. And again, there's a lot of discussion in here. A lot of discourse. In activity 2 is called this 5 + 5 always equal 10. So we continue with this idea, continuous model versus particle model. In that, we do a little lab activity, or now in the instructions of this lab activity, you're told to get small graduated cylinders, 10 milliliter graduated cylinders, put 5 milliliters of water in there and 5 milliliters of alcohol. And then compare, I'm sorry, let me start over. You start with you put 5 milliliters of water and 5 milliliters of water together, and you see that it's 10 milliliters of water. Put 5 milliliters of alcohol and 5 milliliters of alcohol together, you find out that it's 10 milliliters of alcohol. And then you're supposed to put 5 milliliters of water and 5 milliliters of alcohol together and observe that it's actually less than 10 milliliters. And the reason is because the smaller particles fit in between the larger particles. And so it doesn't take up a full 10 milliliters. Now, this is super hard to observe at that scale. So I think anybody who's done this, what we recommend is that you use more than 10 milliliter graduated cylinders, because it's a very small difference. And some students may attribute the difference in volume to like drops of water that stuck to the side of the graduated cylinder, instead of realizing that the actual volume of liquids is different when you mix them together. You can demonstrate the same thing with like pebbles and sand, or sand and water. And sand and water is great. The water goes in between the sand particles, but that doesn't show that. But with water and alcohol, it shows that those liquids are actually made of particles. Now, even though it doesn't show up spectacularly well on live demonstration at small scales, we go to the smallest possible scale for a simulation, and we can see it happening here. So we can see we can add water to, so we can see that they're both X. We had X in each of these, and then you put the water and the ethanol in the same cylinder, and then you cap it and shake it, and they end up being less than 2X. So again, in real life, the change is not this dramatic, but you can see here why it's happening. You can see the smaller particles fitting in between the larger particles. We have a little homework reading on, and this actually involves some visuals as well. So this is, there we go. So this is the teacher key, and we have this homework reading where students look at some different models of water and ethanol, and so they have to visually say which one is the better model. We have a couple different particle models, a couple different, we have I guess 2 of these are continuous models, or at least one of them is continuous. I don't know if you'd call model 4 continuous or particle. I guess it's particle. Okay, and then here's the continuous model. So think about how students would draw this. Which drawing do they think is right? Then in activity 3, activity 3 is kind of neat. We actually determine the mass of air. So you need these little balances. I believe in the interactions kit, we change it a little every year, but they have these, they're like food scales, right? So they're not really balances, they're these little food scales that can measure very small changes in mass. So we take a syringe and we measure it. We just measure the mass of an open syringe, and then you expel the air from a syringe, and you find that the mass has actually changed. You can actually observe the mass of the air, or the difference in mass of an empty syringe versus a syringe full of air. You can also use this to help support the particle model of matter, because students have to realize the reason that you're able to compress air in a syringe or expand the air in a syringe is because the particles are moving closer together or farther apart. In addition to the live lab, we also have a simulation that shows all of this happening. So after doing the live lab, then they can do the simulation. So they can pull, if they pull the plunger out while the syringe is capped, you can see that the air pressure on the outside pushes the plunger back in. And, if you lock the plunger in place, the air will move into the syringe. So you can do all kinds of different little things here, pushing plungers in and out, and you can see what happens when the air is compressed. This wouldn't happen with a continuous model. Okay, you need that particle model because the particles are being pushed closer together. So this is largely about verifying that the particle model is correct. And then there is a reading here about claimed evidence reasoning. And Mike is going to talk about claimed evidence reasoning in a little bit. You close this up with some more discussion, and we have this little interactive timeline, which shows the changes in the understanding in the history of the atom. And we're going to see this timeline several times or a few times throughout the curriculum. And we're going to build on it as we go. So we start with, as I said, Democritus came up with this idea of the atom. And then we see the evolution of the continuous particle model. Then, we had this basic idea of the particle model. Okay, we're not very far. We'll add more to this model in the future. That said, Mike, would you like to take over?
Absolutely. Thank you, Adam. That was a very specific and helpful coverage of investigation 3. I'm going to take over the screen and share what is one way of building capacity within students to write a CER, or claim evidence and reasoning. So let's go ahead and start right here. And what's really nice is that last year's calendar matches almost exactly with this year's calendar. So it was nice to teach the lesson that I'm about to share with you. I got to do the things that the strategies that I am going to share, and I will provide cautionary tales as well as needed. Okay, so let's go ahead and begin. So last year when we did this PD on investigation 3 CER coverage, I had you all put your student hats on, and we ran out of time. So I'm going to just have you observe as teachers, but participate in a way where you think what you think your students will be thinking or what they will be saying. So in activity 1, there's this, oh, sorry, the bell.
Jacqueline Rodriguez, chair coach, please move your card. Jacqueline Rodriguez, chair coach, please move your card. You're blocking. Thank you.
Jacqueline has to move her car. I'm here at campus still, as many of you are too. So activity 1 is about, can you cut the same piece of paper into pieces indefinitely? And I like to make this a little more compelling to students, and I ask them, can you cut a cookie into pieces indefinitely? And I show on a document reader that I cut the cookie once in half, and I say, raise your hand if you can still call this a cookie. Whole class does it. I cut it in half again. Now it's quadrants. Raise your hand if you think it's still a cookie. They all raise their hands. And then I disappoint them greatly, and I cut it about 20 times up and down, left and right. So it's now a grid of crumbs. And then they all look sadly at my projector screen, and I ask, raise your hand if you still think it's a cookie. There's a few persistent ones, but the majority of students, they say it's no longer a cookie. So this is one way to plant the seed that their idea of material things can change when the size of it gets smaller and smaller. And then you can pitch to them the activity 2 question. Does 5 plus 5 always equal 10? Because they're going to observe alcohol and water mixing to make a result that they don't expect. So when you go through this thought experiment, I wouldn't spend too much time on the logistics. I would just use it as a way to get students to participate, look around and find consensus when it comes to agreeing if something is still a cookie or still a piece of paper. You can even get some dialogue with students, asking them what constitutes a cookie, what constitutes crumbs, are they the same thing? And then you can ask them what's even smaller than crumbs, and they'll say dust. But when it comes to atoms, they're pretty much going to stop saying more than the word atoms, at least from my experience, because it requires them to recall something that they've memorized or something that they don't have evidence for. And that's where you come in and ask them, well, what evidence do you have to support the idea of atoms? So activity 1 is a great way to get students to wonder and to be curious. What's the evidence to support atomic theory? Here are some what my students said in a Schoology discussion. I guess if you start cutting actual molecules, you're not going to get that far with scissors. These are responses from distance learning, but they're still relevant today. If it gets very small, it no longer serves the purpose of what paper is. So it is in that case no longer paper. Okay, so now we can start that construct that things are going to be in smaller pieces, but they'll no longer be what they used to be at the macro scale. So when I do this lab in my class, it does get very confusing because of the way the students are mixing the liquids. Maybe they spill, maybe some of it is stuck on the side of the cylinder. So I found this video the most clear and easy to follow for the students. So bear with me, I am gonna play this one time and then place the link in the chat for you to display to students when they are either going to do this activity or observe. So let's go ahead and make this a optimize and observe. Let me know if you cannot hear the audio.
Can't hear the audio, right?
How about now? Oh, it's my Bluetooth. Let me turn off my Bluetooth. Okay, so can you hear me, everybody? Is my microphone? Okay, perfect. So the teacher is pretty much using 25 milliliters of water and 25 milliliters of ethanol because of the way how it's just much more visible, as opposed to using 5 milliliters and 5 milliliters. Once you have a larger volume, it becomes much more apparent in a piece of glass that the meniscus is below the amount you predicted. And so you can go ahead and venture forth and do this with your students. It's a lot of graduated cylinders. It's a lot of ethanol. And it's a lot of trial and error because the technique of the students can mar the data that you're trying to acquire, because sometimes students will get more than what they expected. Some will get exactly what they expected, and some will get less. So I highly recommend, especially if you are in a time crunch due to your bell schedule or whatever it is, show for activity 1.3.2, activity 2, investigation 3, use this video. I also have a video recording of myself doing it in my classroom. Not as easy to follow as this one because she put food coloring in one and the other. Students can obviously see that the mixture is now homogeneous and poured into a 50 milliliter graduated cylinder, and the result is in fact very blatant, right? Maybe even a 48.5 milliliters as opposed to 50. So yes, there will be some modification needed in the language when the assignment says, does 5 plus 5 always equal 10? You can just announce to your students 25 plus 25 doesn't always equal 50. So this video is on the YouTube channel where you can find all of the experiments on video recording, thanks to distance learning. And I'll provide that in the chat. Let's go ahead and go here. Let's go to the channel. And many of you probably have already been in this channel because of the Nearpods or the Schoology quizzes, but this is the interactions YouTube channel. So click on playlists to find all unit.investigations.activities. Okay, so it's going to be in that format. The second video is, let's see here. Let's view all. Where are my, okay, I'll just go to the side here. So this is 1.3.2. 1.1. Let's see. So here's the video of the chocolate chip cookie being cut in class. Also paper cutting, alcohol, and then a video recording of myself doing that. We don't need to see it twice, but that is there for you to have students who are absent to observe, but also students who need to see the same thing over and over, because we all know that there's a few students like that. They just need to see many things repeated often. And it's worth the investment, the time investment that you put into providing video links or a demonstration that you video record, so that, thank you, Ms. Foley, the evidence has to be concrete enough for students to have the agency to put into their CER. I've taught interactions in particular years where we go over investigation 3, activity 2 very quickly. And what happens is when I ask students to place their evidence into a template, they have no idea what I'm talking about. Not all of them, but there's always a group of students that don't have that connection. So once you show video clips, preferably of you recorded, pre-recorded or from the past, then you can have that evidence that is so accessible to you and to your students. And so that is one way to do activity 2 in your class. Just play the video. You can use the teacher that you just watched or my own. And then you can go back to student claims Like if something gets very small, is it no longer paper? So when you ask questions to students to either redirect their misconceptions or to engage them or to assess their understanding at the end of the class period, you can use questions. You can ask them to support what their classmates said, or what is what's inaccurate about with what one classmate said. Maybe you want to make it anonymous. Maybe you want to take it from another class. But that is one way to continually get students to be drawn to the evidence, as opposed to just saying, fill out the data table, turn it in, and then don't leave when the bell rings, because the teacher doesn't dismiss you. The bell doesn't dismiss you, the teacher does. So try to keep in mind that when interactions is being taught, it's not very linear. It's going to have to depend on the quality of the evidence, the way it was delivered, and how your students are receiving it. And so after our break, you'll see, how do I address student low performance? How do I address consistent low performance? And I hope that it will resonate with a lot of you who had a day like today, or great days or not so great days, or just being prepared for the future. What is to come when you teach activity 2. Now, activity 2 also comes with a simulation. Adam provided that in his presentation. It's really one of interaction's greatest strengths to have a phenomenon and then a simulation that resembles the phenomenon. I still haven't seen too many curricula like that. Some get kind of close with PhET, some get kind of close with CK12, but interactions, it's so explicit. It's 2 containers, 1 alcohol, 1 ethanol. They're different shapes and nothing else. All the extra stuff that PhET tries to sneak in for college research, or for college courses, or for graduate courses, all that is gone, because we know students can get so distracted so easily. Or they'll ask, hey, what's that? Or what's that? And then now the lesson's going awry. So when you have these very minimalistic simulations for each activity interaction, you can get students to focus on what's most important, as opposed to trying to explain everything. And then you have a group of students rolling their eyes, falling asleep, taking their phones out, and not learning. So this simulation is really powerful to have students. You can even do a see and wonder activity. Put this into a Schoology quiz or warm up and just ask them, what do you see? What do you wonder when you explore it? And then have them connect it to the video clip. Okay, once again, right there's the value of the video clip. You can't go back in time and have them do the experiment again, but the video clip is something they can look back and say, oh yeah, that's right. When the 2 were combined, they did not equal 50. And what's awesome about the simulation, it doesn't give you specific amounts. So you are going to be able to use different amounts if you wanted to do a demonstration or have a modified class activity. So this is very helpful because it's different colors and different shapes. Students can see that the gaps are filled between the 2 particles of ethanol, and maybe that's why it is less than 50 milliliters. So that is one piece of evidence students can put into a template. I'm going to go ahead and show you where this is all going in case I'm losing some of you. So in today's presentation, there's going to be 3 templates that you can use for claim evidence and reasoning. And the first box can be filled with the alcohol and water phenomenon. So this is the first template. All right, so everyone go ahead and join there. And this is something I like to use because it's easy for students to follow. I tell them, go to row 1, everybody. All right. are you going to agree or disagree with this prompt? And the sample prompt can be, it could be, does 5 + 5 always equal 10? It can be something as general as, is there sufficient evidence that atoms do exist, right? This is something that's nice and generic, so you can use this for all activities. And then the students can either say, yes, there is sufficient evidence, or no, there's insufficient evidence for these atoms. And then they can cite the activity that they just did, not a presentation topic. I'm definitely repurposing this for other units in addition to interactions, but this can be the phenomenon, and explain why your phenomenon is so compelling. So you've got your claim, you got your evidence, you got your reasoning, and then some students can go beyond. Unfortunately, most of mine don't, but I do want to provide this for rigor for those who are willing to go the extra mile and explain another reason why the evidence is compelling. But then they follow it up with row number 5, rewrite your claim here in another way. So yes, it's very formulaic, but it's so easy to grade. It's so easy to facilitate when students are doing this for the first time. And it's, you can use this for any claim, evidence, and reasoning topic. So that is one template. And so the students would say, yes, there is sufficient evidence for atoms, because in the alcohol and water video, the total of 25 + 25 equaled 48.5 milliliters. And this is compelling evidence because there are gaps between molecules proving that materials are not continuous. Or if they, let's say a student was writing it, they could say something like the particles fit in between the other particles. So that's evidence to them. They might leave row 4 blank, and then they could say atoms are the real deal or something like that at the end. So have fun with this, be flexible, but know that I found a lot of use out of this, teaching this in chemistry and in interactions. The second template, this one is something the science leadership team uses, and it's a little bit more encompassing. Let's put this in the chat as well. This is template number 2. Second template. And everyone click on that. Oh, I already had it open. So you can have the students write the overarching question of the unit and then jot key ideas as they are learning the science throughout the unit, and then the claim to the driving question, 3 columns of data, and then the reasoning. So very broad, but very powerful because it will connect all the components of the unit. And then the third template is something that I just used 2 hours ago with my students, and that is having multiple pieces of evidence to support a single claim. So this is the third template. After this, I'm going to we'll go on a 5-minute break, but go ahead and take a look at this third template. And this one has the actual prompt I used today in class. And then the students would, so for some students, you have to really make it clear that it's a yes or no statement. So I put in a slash, students, yes or no, atoms do or do not exist. Okay, they mostly all end up putting yes, atoms do exist, but then they have to just follow my steps, and then they can, it's just like the first template, but then the second box where it says box B is the second piece of evidence. So in activity 3, the students are weighing the syringes with air and compressing the syringes with air to provide evidence that air is made of particles and air is made of empty space as well. And so these pieces of evidence can also support the claim. And then the third one is, so one is about mass of air and the other one is the empty space in air. And so this is almost like an essay. It will take longer to grade. So maybe this can be something that you make as a culminating task if you want, or something that is going to be maybe every 2 weeks or every 2.5 weeks. But it's provided to you. But this is all hinging upon the buy-in that your students have towards the evidence. If they see how much you invest into the evidence and how clear you're going to make it for them, then they will remember and it'll be easy for them to use. So that is how I teach claim evidence and reasoning in a nutshell. Let's take a 5-minute break, everybody. And I will set a timer. 30 seconds, everybody. And time. Let's return back. Our next agenda item is overview of investigation 4. Adam, are you ready to take the reins?
I am.
All right, there he is.
I have students or a student building a robot in my class, and I stepped away to consult a little bit.
Welcome
back.
back.
Uh, now I think I have cleared up what was slowing my computer down, so I'm going to try this again. I'm going to try to share my screen again because there are a couple of things that I want to go over on the website, and also on Schoology. Those two things are linked together. Let's see. Okay. So share screen. Here we go. So let me share this link again. This is on the Interactions website, and it is the page called Planning Resources and Guides, as you can see on the very top. There we go. So there's a link. And in fact, I want to go over this whole curriculum section, as I said before. So let me start with the curriculum section. We already saw this, but I started having problems. So I showed you the things on the main curriculum page, is overview type stuff. The planning resources and guides is also kind of an index to what's in the curriculum section. It's an overview of the whole curriculum with links to, as I said, the Schoology Nearpod and Google resources. But we also have this suggested pacing plan here. I'm going to see if I can enlarge this a little bit. So this suggested pacing plan, it's for many different schedules. This is the pacing plan you might want to follow if you want to make sure that you cover all 4 units. Most people don't cover all 4 units, but it might give you an idea of, maybe how your pace is compared to the overall pace. But I think generally speaking, it's better to go too slow than too fast. But you can see that we've broken it down so by investigation. So we have a 180-day schedule, a 16-week schedule. If you're on a 4x4, then your fall semester and your spring semester are very different from each other. Your spring semester is 25% longer than your fall semester for some strange reason. So we have a 16-week schedule if you're teaching it in the fall, and a 20-week schedule if you're teaching in the spring. And then we have a 5-week summer school schedule, pacing plan. So you can use this as a guideline, but don't feel that you are bound by it. There's also this was posted for 2020 summer school, but the curriculum map is still valid, and summer school is summer school. So this is another guideline if you end up teaching interactions in summer school. And then I mentioned we have the student workbooks in Google Slides. So we have a page here that has links to all the units in Google Slides. Now, the nice thing about using these, if you choose to use them, like I said, we have multiple ways to present the content. If you choose to use this one, then it will, what you can do is you can assign this using the Google Drive assignment app on Schoology, and then it will make a copy for every student. It's more than just a PDF though. So it is posted in Google Slides, but we also have navigation tiles up here to help go page to page. So the student doesn't have to actually interact with the slide sorter in Google Slides. They can just go page to page up here. They can type in any box that is shaded, like the student name box, they can type in. And they also have a table of contents with links on there, so you can jump ahead to different links. Now, the value of this, if you choose to use it, is that students can write. Now, this is taken straight from the PDF. It just has a few enhancements, like the navigation links up here that can go from page to page and go back to the home. But so just as students would write in the book, they could write on this Google slide. You can monitor this in real time, because if you assign things to the Google Drive assignment app, you can monitor student work in real time. So we have ways for them to draw models in here, to answer questions, and the entire book is in here. So they can draw on the models. I think there are also, there are also links to the simulations. You see, you can jump right to the simulation from the book. That's one resource. If you like it, you may use it. There's another one where these Google Slides were then taken and put into Nearpods. Nearpod is more interactive than Google Slides. So these are each separate files. So you can add all of these. There's a little video introducing Nearpod. If you've ever used Nearpod, then you know it's really a great way to keep students with you as you go through a lecture. So Mike has shown Nearpod before, and he's showing you how you can use these. But I wanted to show you that they are all indexed on the web page here. But I want to go back to the planning resources and guides. And I will get into investigation 4 in just a moment, but there is something that comes before investigation 3 and before investigation 4, which is the Unit 1, Part 1 summative assessment. There are 6 summative assessments built into interactions. They're not required. Some people just want to do the textbook, the Schoology questions, and base student grades on those. But if you want summative assessments, there are 2 in Unit 1, 2 in Unit 2, 1 in Unit 3, and 1 in Unit 4. So once you get to the end of investigation 2, you might want to do Unit 1, Part 1 summative assessment. Notice that this web page, anybody can access this web page. This is not secure in any way. So students can access this web page. That's why we don't have any answer keys. We don't have anything that needs to be confidential on this web page. Anything that should only be available to teachers, we put in the Schoology group, and then we put a link to it on the web page. So if I click, as I did, Unit 1, Part 1 summative assessment, it takes me straight to the summative assessment in the Schoology group, which you can then add to your courses. Now, the assessments are not, they're really not just recall of the investigation. They test the concepts without just having students show that they can memorize, that they've memorized things. So this question, for example, in order to answer it, students need to it says, okay, you have these two cars, one is positively charged, the other is negatively charged. What's going to happen when you pull the wedges out that are holding the wheels in place? Well, if a student understands that opposite charges attract and like charges repel, they're going to be able to answer this, that the cars will move toward each other. But they're not just reproducing what they've learned in the or what they've seen in the lesson themselves. So you can see that we see how the strength of force changes. So that's a question about fields, and then a question about force. So these are NGSS focused questions, and then when we do have a model. So we have a video of the wig on the Van de Graaff generator, and that's embedded in the test. And then we have a way for students to draw a model of this. So they draw a model of it, they upload their using Google Drawings. If they click this image, it will open a template on which they can draw a model. Okay, so it opens this template for them. It says exam copy on it. So they can't just pull up their old Google Drawing that they did, 2 weeks ago and turn that in and say, hey, I did it for the test. Right? So they can draw the model on here and then submit and then download and submit it. And so there is some modeling in there. And this test is available. There are a few more questions. This is again, this is showing the like charges repel. This is showing, because we use balloons and rods, this is showing what happens with those. And then this is again following up on that balloon and rod question. So if you use the test, we do have a survey we would like you to complete after administering the test. So I realized that we need to add that to our website. So underneath each, I guess I'll put it after. So right after the summative assessment, I will put a survey for the students and a survey for the teachers. So this is very helpful to the district to just collect data to justify the program. So if you do use the summative assessment, please look for the survey links. If you already gave the assessment, go ahead and give the survey. And then we'll have one. We'll have a new survey after each assessment. They'll be posted on this page later tonight. So now let's look at investigation 4, the planning guide. Investigation 4 is about the history of the atomic model. So we've established that we've established fairly well that the particle model is a thing, right? At least more of a thing than a continuous model. So now we go over the history of how that model was developed. This is really one of my favorite topics to cover in chemistry, because it really shows the nature of science, that how the model changed from one discovery to the next, and it was really developed over a period. The atomic model was developed over a period of a couple of decades to go from the discovery of the electron to the Bohr model, and then a couple more decades to get to the quantum mechanical model. So it's gradually over time, but it's not a tremendously long time when you look at the historical context of all this. We start out with this first activity. What are the particles that make up all substances, and how small are they? You'll probably have a lot of students who know the word atom. And I kind of encourage you to not use that word atom, because they all have a perception of it, and most of their perceptions are very flawed. talk about particles, talk about interactions. And eventually we're going to get to atoms and molecules. But hold off on talking about atoms until you get up to this point in the curriculum. We talk about the driving question. Students will draw their idea of what an atom looks like. So this is their initial model. Then we go into, again, another timeline, but we build on it. So we started out last time, we just kind of established, last time we looked at this timeline, we just kind of established that the continuous model and particle model were two competing models for understanding the atom. Okay, mine's loading slowly, so I won't make you wait. If you want to see the timeline, please click on it. In fact, I think this might be, is this the bad link? Sorry, this is not us that changed it. The people who write the curriculum actually moved their timelines to a different system. So I guess I have to update that link, but you can access it through the Schoology assignment itself. Oh, and again, let me share this link. Sorry about that. Oh, I see. It was shared with waiting room participants. Somehow I ended up sharing it with the wrong people. Okay, there we go. So that's the link to the doc I'm on right now. But again, it is accessible through the website. We have this scientific notation activity. It's good for students to understand scientific notation, but they're not going to use it a whole lot. They're going to have to learn it in chemistry. So if you are finding it hard to keep up the pace, you know, it says it's optional. I would probably opt not to spend a lot of time on scientific notation. The reason is in interactions, it's more conceptual. We want to focus on the concepts. In chemistry and physics, they're really going to need to know scientific notation. So then we have this activity of how small are atoms, and we compare the size of atoms to a bunch of other things, basically. Like if an atom were this big, then so the diameter of an atom is some tiny amount. And then we say, oh, well, if an atom was I believe it's nonpareil, I don't know if I'm pronouncing it right, pareil. They're the little sprinkles on cookies or cupcakes. So if we say if an atom was the size of one of those sprinkles, then DNA would be about the size of what? And they're doing a little bit of math. So they figure out, well, what is the proportion here? This is how many times larger than this. We say this, so they figure out how big DNA would be, how big a virus would be, how big a red blood cell would be in a strand of hair. We want to get used to using that term particle and really get an idea of what atoms are. After that, we move into activity 2. Activity 2 is the mystery box activity, and this is based on J.J. Thomson's discovery of the electron. Now, J.J. Thomson used cathode ray particles to, he used a cathode ray tube, which sends a beam of what looks like a beam of light. Not exactly a beam of light, but at the time, nobody really knew exactly what it was. They had an idea, but when you run a current through a cathode, you get this beam going through there. And what J.J. Thomson found, he did a lot of experiments with these cathode rays. And without actually being able to see what was there, he could see, well, these these beams, these colored beams, they're coming off of metals, they're flying off of metals. They're able to knock down a little target, so they have some mass. When he put a charged plates above and below them, he would see that the beam, the ray, it bent toward the positive plate and away from the negative plate. So what he discovered was electrons. He took several different pieces of evidence, and he said, okay, the current model of the atom, which says that the atom is just this ball, is not correct. The true model of the atom is that this ball is positively charged, but it has a bunch of these negatively charged electrons embedded in it. And that's called the plum pudding model. So students, they learn more about cathode ray particles. Sorry, they do this mystery box activity. The mystery box is where they shine a laser through the box that you see on this image. They don't know what's inside the box. They try to use indirect evidence to figure out what's inside the box. So they shine a laser through some number of these holes, and they try to guess what's in there. And you don't have to tell them what's in there. I think partially full water bottles work really well because they both block the lasers, and if the laser hits it right, they scatter the light. So when they see the laser coming out of the back of the box, they come up with different predictions. So they start with the mystery box where they have the light going through the box, and then they move on to simulations of the cathode ray tube itself. And this talks about J.J. Thomson's discovery of the electron. So here we have a simulated cathode ray tube, and we have no matter what electrode they use, they find out that the behavior is the same because the electrons are the same no matter what atom they're in. And we can see that the strength of the charge on the charged plates above and below the ray causes the ray to bend relative to the charge. We can look at electrons as well, or particles as well. And then we have another interactive in here. And this interactive shows cathode ray particles. And you can change and then you can also send charged atoms through those plates. And so we see that charged atoms don't react the same way that the cathode ray particles do. And the cathode ray particles are charged, they're negatively charged, and they're much, much less massive. In the next activity, we use a series of simulations, and this focuses on Rutherford's gold foil experiment. In Rutherford's gold foil experiment, he discovered the nucleus. So this is essentially, J.J. Thomson's model is this positively charged mass with negative charges embedded in there. So Ernest Rutherford, he expected when he shot a bunch of alpha particles through this gold foil, and based on J.J. Thomson's model, Rutherford expected the particles to travel through the atom just like this, because there's very little in this model, this plum pudding model of the atom, there's very little to stop something. An alpha particle is pretty massive. It's a nucleus. It's pretty massive and it's positively charged. So they go through with a certain amount of force. But what J.J. Thomson found was that when he, or not what J.J. Thomson found, what Ernest Rutherford found is when he shot alpha particles at the gold foil, most of them went through, but some of them were deflected sideways, and every once in a while, one would be bounced way off. Like here's at a 90-degree angle, sometimes one would bounce way back. So Ernest Rutherford said, well, that plum pudding model is no good. He incorporated what J.J. Thomson discovered into his model, which said there's a positively charged nucleus. Most of the mass of the atom is in the nucleus. So, going a little too much into the atomic model, but this is what students are discovering by looking at it, by engaging with all these simulations. In the fourth activity, the fourth activity is more about modern model of the atom, and this just says that you can't really draw an atom like the modern models of the atom. We don't draw electrons because they use this dartboard simulation. So they throw a bunch of darts and they see where the darts would land, and we see that there is a darker area near the middle, a lighter area on the outside, and so this represents a probability map, and that's what we use to draw atoms now. We can't locate the exact location of an electron. So because electrons move very erratically, very fast, they're very small, and they can't actually be located the way that we like to draw them. So this introduces the idea of a probability map, and there is this reading on the short history of the atom. And I think these simulations are great. When I teach chemistry, when I get to this unit, I use a lot of the interaction stuff to teach this section of chemistry as well. So, Mike, back to you.
Thank you, Adam. Right on time. So I love how Adam's planning guide is a one-stop shop for all of the curriculum and the tools and the teacher guide, like the explanations. I remember teaching interactions the first year, second year. I always needed to know what's the big picture that I need to, that is the trajectory of the unit or investigation. And these planning guides, they have it all in one page. So thank you again for shedding light on it and actually constructing these. Adam is the author to these planning guides. Our next topic is how could teachers respond to consistently low performance? So let's go ahead and share the screen and get to that slide. So it was right here. So what I've learned from distance learning, the hybrid model and in-person teaching is that it's a very slippery slope to say, oh, this entire class is low performing or this entire class is high performing. It's better to try to get more specific about the groups within the class so that you can address those groups specifically and more effectively. And then those who are already showing proficiency in that class can receive enrichment or can set the standard of rigor for everyone to strive towards. So just because there is an achievement gap, an opportunity gap, a lack of access and equity in some parts of our lessons, there can be those students who can still drive the rigor, because we know that a high tide rises all boats. Now, that shouldn't be taken to the extreme, but we should try to avoid all extremes is what I'm pretty much getting at. So when you have this low performance within a class, I try to track every 10 minutes, every 20 minutes, if the students are paying attention or if they are checked out already. And that's in some ways easier to do distance learning because you can just send out a survey or do it on a Nearpod where you get instant feedback. In the classroom, we can read body language. We can obviously see it when a student's on his or her phone, or if he or she is sleeping and or has the head down. So try to look at your class as a, a, a class that has groups of students. You can even think of it as chunking. You can chunk your class into who is proficient and who is not, and then try to look for the most common misconceptions. And I'll show you some examples of what some students have. They have misconceptions of what a claim is or what a claim does. And once you find the common misconceptions, then you can address those as opposed to trying to find the individual need of your 200 plus students. Modify the original lesson plan to meet the need in step 3, and then include an assessment task to help you keep track again. After you've modified, then you have to reassess to make sure you are not repeating the same instructional oversights, but also to make sure that those who have now risen from below or near proficiency to move on to mastery, as opposed to dwelling among the nearly proficient level, and then modify your future lesson plans. So the model that I'm following is from equitable grading and instruction. It is this diagram. Surprised I put it so far into the slideshow. Adam knows I love slides. So here is the diagram. So you do your instruction, and then once you get your, you can call it, I'm not going to use the word disillusionment. I'm going to say the word of reality. When reality hits and you find out, oh, I have low performers and a large group of them, then you can go to corrective instruction and then formative assessment. And then those who do not need the corrective instruction can go into enrichment. So this could be retitled as EGI. I hope I didn't date our presentation, but those who are familiar with equitable grading and instruction, you know that it's about having students not be discouraged and have like a learned helplessness in the class. So I will be showing a short video clip of something I just discovered this week. It is an old social experiment that was done in a classroom. Maybe you've seen it before. When I found it on YouTube, it was 9 years ago. So Adam, if you could have that loaded and ready in about 10 minutes, really appreciate it if we could play that, since my laptop has the audio issues. Oh, you just sent me the text, the message. Thank you, Adam. Okay, so let's get to some examples of low performers so that you can get a clear idea of what's one way to respond. So a common misconception is CERs, a claim. What is a powerful, compelling, yet concise claim? So when I ask the students, is the paper still paper after it is cut indefinitely? This is kind of, these are like the responses that I get. I think the same as before, because all these experiments support my original ideas of particle models. Another student might say, after the activities we have done, I still believe that paper is still paper regardless of the size until the different elements that make up the paper are separated. I still agree that with this because it is similar to the particle model of matter, which I think was the best representation of things and experiments we have done regarding matter, like with liquids and gases. And finally, I would say that eventually, if you cut the paper enough, it could not be identified as paper because there are certain characteristics that it must pertain in order for it to be considered paper. I could use the evidence previously stated about the water and ethanol mixing and the air particles in the syringe to properly explain my thinking. Wow, these students are very confident. but that doesn't mean that it's an effective claim. These students were asked to provide evidence. Now, this is before I used my template. Students that write claims that have these references to all these experiments, or the things and experiments we have done, or phrases like evidence that's been previously stated, it is not using a connection. There is not a connection between the statement and the evidence. Sure, they're referring to some evidence, but it is not a clear connection. Like students could fake, they could be absent and they could say, oh, we had an experiment about liquids and gases. Oh, there was ethanol and water mixing. Maybe they do know, maybe they do know the connection, and they just didn't know that I wanted them to be more explicit. So when you get students with this misconception of what a claim is, you have to spend the time to unpack it and refer to your expectations of what is a powerful claim. So when students can see that their claim has not received full credit, or I am continually showing examples of how something could be improved in class, then they can start to implement change. And I first need to see, do they understand the connection of the evidence to their claim? So this can be done very easily in Nearpod. It could be done in a class discussion. It could be done in a Schoology discussion, which is what I call waterfalls in my class. And then the students can see, okay, it's not about just saying ethanol and water, like it's a magic phrase that gets you full credit. It's not about referring to the representations of liquids and gases. It's going to be a reference to the mass of air was 0.01 grams. The mass of air was 0.02 grams. And that supports my claim because air has mass, 0.01 grams. Therefore, air has atoms. Therefore, air is not visible, but it does in fact exist as matter. And so you have to have students revisit this. Otherwise, they're going to continually use this as a misconception for the next claim, because the next claim is, why do things in Unit 2, why do things explode? And they're going to use the same type of poor work habits, where they're going to say, oh, it's because of the Van de Graaff generator and the Bunsen burner. It's like, no, that's not why things explode. It's because of the potential energy in the Bunsen burner that allows that is activated by the spark of the Van de Graaff generator, converting it into kinetic energy and thermal energy. So you see how students can get deeper and deeper. Maybe this is a great introduction to the claim, evidence, and reasoning like journey, but they can't stay there. Otherwise, you'll continually get more and more vague claims and vague evidence. So you could actually ask a different prompt so that students can try it again without just regurgitating information. Here's an example. Is water and alcohol made of the same particles? Well, if they're going to answer this prompt, they're going to have to say explicitly that the water molecules are different sizes than the alcohol particles, allowing them to fit between the gaps of the other molecule. This tells me that atoms are real because of what water and alcohol are made of. Another prompt is air made of nothing? Right? So simple. And they could say, no, air is not made of nothing. It's made of atoms that weigh 0.01 grams. And that tells me that the paper, if it's cut into smaller pieces, it's going to be atoms. So use alternate prompts if you want to address misconceptions of the student claims so that you can get more and more specific and more compelling claims with explicit connections. Another low performer, low performance in my class is lack of participation. So distance learning, hybrid learning, and then now I want to call this year the aftermath of distance and hybrid learning. I don't know how your work habits are of your students. I promise not to rant. But I find more challenges in the student motivation than I have in my 15 years, because maybe that's something they just kind of picked up to survive and not give themselves a hard time why they're performing low. Like this lack of participation. I did a survey in distance learning in one class where I had 18 LTELs. Can you believe that? 18 LTELs in one class. I surveyed them and I asked them, why don't students ask for help? Why do they just give up? And thank you, Danielle. 10 out of 18 students said it's because they're ashamed or they're shy. 4 out of 18 said that they were indifferent. And then a few others said that they were other reasons. But the in-person instruction might be exacerbating the shame, embarrassment, and shyness, because you can't hide and turn your camera off. You can't hide and say, and then just not respond, pretending your microphone's broken. There's nowhere to hide really in your classroom in person. So maybe the lack of participation is magnified. So I remember creating an encouragement slideshow assignment where students who feel embarrassed or discouraged can just do these things. And it did help because it was a fairly simple task. So the whole class was 25 students, 18 of them LTELs, and then 20 out of those 25 were able to do the task. So that was way more participation I was getting than most assignments in distance learning. And so once students start to see that they can be part of the conversations and part of the excitement or curiosity or of the topic or anchoring phenomenon, then you've got them. They have agency to participate. There is this video that I want to show you about learned helplessness that Adam's going to play on his audio and his shared screen. It's about 4 minutes long. At the end, I want you to answer this question right here. How might this video impact your response to students who are indifferent to our instruction? Let's actually modify this a little bit. If you can give me one more second, Adam. Indifferent or resigned. Okay, so keep this in mind, and you can answer this in the chat or unmute your mic. And looks good, Adam. Go for it.
Everybody have one? If you would, just do them one at a time, and I will tell you when to do them. Everybody turn it over. Just do your own work. And this isn't meant to be hard. These are anagrams. Just do the first one only. Go ahead and solve it. An anagram is rearrange the letters to form a word. Just one. Just rearrange those letters to form a word. When you're done, I need to see your hand raised. Okay, keep going. We'll wait. Keep your hands up, please. Just do number one. Don't go on. Don't go on. This isn't meant to be difficult. Okay, put your hands down. Let's just go to number two. Don't even worry about number one. Go to number two. Solve that one. Again, when you're done, I want to see your hands up. Everybody's hands down. We're going to go ahead and do number 3. For number 3, rearrange the letters, and as soon as you do, go ahead and put your hand up. Here's what you need to know. You were both given 2 different lists. This side of the room was given these 3 words. And left side of the room, here you go. They were given bat. What would the word be? The second one, they were given lemon. Brian, the word? Melon. They were easy. The trick here was both of you were given the third word, which was the same. The third word was cinerama, which was American. Your first 2 words on this side of my classroom were not solvable. They were impossible tasks. I'm sorry. I know, but here's what we did this for. I was able to induce something called learned helplessness in the left side of the room very easily within about 5 minutes. I want you to think about what happened to you, this left side of the room, when you saw the right side of the room raising their hands because they already had the task done. What happened to you during that time? Jory?
Felt stupid.
You felt stupid? Okay.
I felt rushed.
Felt rushed? Joelle?
I was even more confused.
You were even more confused because they all got it and you were still struggling. Chelsea?
Frustrated.
Frustrated. What happened by the time you got to the third word? Because I'm here to tell you, this side of the room is not significantly more intelligent than this side of the room. That was a random assignment. So what happened to show the differences? Why did you have more of a difficult time with the third word, which was the exact same word? Brian?
My confidence was shot.
What you experienced was a term called learned helplessness. How many have heard of the term before? Let me see your hands. Learned helplessness is often used in the academic literature to mean what? Jory?
Basically, they fail once or can't do something one time, and then they apply that to everything in the future, so all the future applications become skewed by that learned helplessness.
And here's the thing, and this is what I want everybody to understand. It's usually only used in the academic research. You'll see it in ed psych books. You'll see it in school textbooks when they talk about learning. But I'm going to challenge us to think about how learned helplessness can actually apply to the social scene. Can someone give me an example
Okay,
of
we
how
could
that
stop there.
might
If
look?
we could stop there.
Tasha?
Thank you, Adam. All right, so how might this video impact your response to students who are resigned or appear indifferent or are indifferent to our instruction and assessment? Can we hear from like 2 or 3 teachers? If you're still there. Okay, so Danielle says more patience and compassion. Thank you, Danielle. Any others? Any other insights to learned helplessness in our classrooms? I see Miss Foley on camera. If you could share with your microphone, I'd appreciate it. You're muted. Oh, I can't hear you. Okay, maybe you can type it. There's a few more in the chat. Give them something that they can accomplish to show they can. Compromise. Accomplish the work at some level. Thank you. Thank you all. And so, I hope this anecdote kind of stays with you, where whenever you encounter this indifference or resignation or even like lack of excitement, because the students have maybe were taught in a different way, or they have different experiences, or there are different challenges that kind of make them unequal to other students that see it so clearly. Maybe it's resources, like getting the easy anagrams. There's some more in the chat. Offer opportunities such as anonymous mailboxes where students can ask questions they don't know. I love it. And so you can at least address their needs the next day. there's a request for the link to the video. Adam, if you could go ahead and share that with the group. And it's actually a 6-minute video, but you can start at minute 1 and end at minute 5 if you want just that sweet spot of the video. So so that's kind of like the overarching lens like I wanted to share. There were more specific parts of this presentation, such as the how to become more proficient in atomic theory, or what do you do when a project fails. But that's the same material that I covered in our video recording last year around the same time. So you can look over these slides and look at what to do if there are other challenges where you feel like low performance could be the instructor's fault, or the environment, or the timing, or a combination of everything. Usually it's not just one culprit. So I hope that was helpful. When you get low performance, try to keep this video in mind. I keep repeating myself. So one more feedback in the chat says, I may try to ask for more feedback, show them individually that they're able to solve this on their own, and encourage making mistakes. Absolutely. Like, our voice can really stick with them in their heads. And if it's positive and encouraging and providing hope and insight, then that can actually go a very long way. Like, I always ask students, who is a teacher you've been grateful for, like in your, that you'll never forget. And the overarching theme is always like the encouragement that the teacher believed in the student. As cliche as this may sound, but the students always write about this. It's like, write a letter to a teacher you're grateful for, and then they'll say, this teacher, and it's because of these reasons. And it's always that that belief that the teacher had in the student. And so if we identify learned helplessness, we can break through. All right, getting a little emotional here, but let's go on to our surveys now. So there are 2 surveys Adam and I wanted to provide to you at the end of Unit 1. One is something called the Interactions Post-Assessment Teacher Survey. So this is in no way to track who is a successful teacher and who's not. This is to see if our PDs are helpful or not. This is to see how do you feel at the end of the unit? Do you feel like you understood the necessary science concepts of the unit? Do you feel like you can teach the science concepts for the next unit? Do you feel like you're able to provide effective instruction? Are you able to provide effective instruction for the next unit? As an interactions teacher, I feel like that I'm part of a professional learning community. LAUSD provides effective support for interactions. So this is for IHAM. Maybe it has something to do with the new superintendent. I don't know. But please fill out this post-assessment teacher survey when you finish Unit 1, Part 1, Unit 1, Part 2, and the other parts in these bullet points. So links to the surveys are now posted on the websites next to the assessment links. Thank you, Adam. And then for your students, this is for your eyes. Your eyes are to look at the student survey, but Adam and I will also get this information as well, is that the students can meet the learning targets that are in the website. What is their confidence level? What is their proficiency level? This is like reflective. So this is a subjective survey that students will indicate. And then when Adam and I see this information, we can know what to focus more on in terms of coverage and depth. And for you as a teacher, you can see what you might want to change or modify or emphasize again in your instruction. So thank you all for being here. I'll go ahead and put our evaluation for today's PD, different from the surveys in the website. This is just for today. And I know for sure that IHAM renewed our, oh, so you want the post, okay, so the link to today's PD evaluation form is this one. And then the links to the surveys, Adam, should I put them in the chat?
You can, or the surveys are
They're in the-
posted on the planning resources and guides page. Yeah, there you go.
Okay.
Show where they are if you scroll, or if you go to the planning resources and guides page under curriculum, you can show where they are. Because there's a different survey for the students. The survey is different for each assessment.
Ah, yes. So
Okay.
that is a very good point. The surveys will be time specific, like Adam said. So if we go here, there they are. Post assessment survey. So I'll put this link in the chat so you can get a time when to give the surveys as well as access to the surveys. So this is the scheduled survey.
Can I also add, Mike, we wanted the surveys to be anonymous, so the students should know that these are anonymous surveys. We're not collecting their email address or anything. If you for some reason wanted to see how your students responded, you could send us an email after your students complete the survey, because we don't know what teacher they came from. We don't know the students' names, but we do know what time they were submitted. So if you let us know that your surveys were submitted on this date at this time, we could share results with you if you're interested.
Thank you all for being here. You are free to go. Adam and I will stick around for 15 minutes to answer any questions that you might have.
So there's no sign out, just the evaluation?
Yes.
Thank you.
A quick question.
Yes.
For the kit that I have, it seems like for the whole first unit, there was missing items from the kit,
Okay.
and it was making it very hard for me to do any of the hands-on activities. It was more so just watching videos,
Mhm.
trying to connect the students to that. Is there any way that, as I'm looking through the rest of the kit, just if I am missing one or two items, do I request that, or how would I go about getting those items?
So the kits they're not complete. Adam and I, we provided, Adam, can you stop recording? Thank you.
Hold on.
It says recording.